Hello my curious friend, and a very warm welcome to Deepfield Channel. Tonight we are going to contemplate something you have likely done dozens of times without realizing the profound depth of that simple gesture. Lifting your eyes to the sky and gazing into the past. Because that is exactly what happens when you look at a star. I am not just being poetic out of a habit, I promise. I am being entirely literal. And I also promise to try not to make this mystery so unsettlingly beautiful that it keeps you awake, although I cannot guarantee anything. But before we dive into this journey through time and light, I would love to know in the comments which corner of the world you are listening to me from tonight. And if you are feeling too lazy, just leave a simple hello. It might seem like a small thing, but that little gesture shows YouTube that our space here is welcoming, and it helps us bring more tired minds to relax with us. If you enjoy our scientific journeys, please leave a like and subscribe to the channel. And to those of you who are already part of our community, my deepest, most heartfelt thanks. If you want to get even closer, consider becoming a channel member. Members get early access to videos before anyone else. The link is in the description. Now, wherever you are, find a really comfortable position. Adjust your pillow, drop your shoulders, let your breathing slow down just a little. If sleep comes during our conversation, accept the invitation without any guilt. Let us begin. There is a scene that almost every human being has experienced. A clear night sky, far enough away from the city lights, and suddenly that feeling that the roof of the world has simply vanished. The stars appear little by little, as if the darkness were a canvas and someone were piercing tiny holes in it one by one, letting light shine through from the other side. You have paused in this moment, perhaps as a child in the countryside, perhaps on a trip, or maybe just during a sleepless night in your backyard. And almost certainly in that moment you thought something like, "What a small place I occupy. What a vast thing all of this is." What rarely occurs to us in that moment is the strangest question of all. Not how many stars are there, not is there life out there, but rather a much quieter and far more unsettling question. What if what I am looking at no longer exists? It is an idea that seems absurd at first glance. You're looking at something. Your retina is registering real light. It is not an illusion, not a painting, not a dream. The light has reached your eye, crossed the atmosphere, and activated the cones and rods at the back of your eyeball with irrefutable physical precision. How can it be that the source of this light no longer exists? The answer lies in a property of the universe that our everyday intuition simply cannot absorb naturally, because nothing in our daily lives has prepared us for it. Light has a speed. And this speed, although incredibly high for anything you have ever seen moving on a soccer field or a running track, is absolutely insignificant compared to the distances the universe has adopted as its standard. Think of it this way. When you turn on the light in your room, it seems instantaneous. When lightning strikes a kilometre away, you see the flash before you hear the thunder, but the light seems to have arrived at the exact same moment the lightning struck. In your daily life, light is synonymous with immediacy. It seems to have no delay whatsoever. But this is an illusion created by the scale of the environments we inhabit. Light travels about 300,000 kilometers every second. 300,000. To cross a room, it crosses the entire Earth more than 20 times. For it to go from the Earth to the Moon, it takes about 1 3/10 seconds. It seems too fast to matter, until you start working with the real distances of the cosmos. The closest star to us, other than the Sun, is called Proxima Centauri. It is about 4 light years away. A light year is not a measure of time, it is the distance light travels in an entire year, moving at 300,000 kilometers per second without stopping. If you try to translate this into kilometers, you will end up with a number with so many zeros that it loses all meaning. But what really matters is this. The light leaving Proxima Centauri right now will only reach your eyes 4 years from now. When you look at it in the night sky, You are seeing it as it was 4 years ago. Not today. 4 years ago. This alone is enough to make you feel slightly dizzy. But Proxima Centauri is our immediate neighbour. The observable universe has an extent of about 93 billion light-years in diameter. There are galaxies we are seeing today whose light left over 13 billion years ago, when the universe was still crawling in its most remote infancy. There are no everyday words for this, but there is a very concrete and very silent consequence to these distances. A star has a lifespan. It is born, burns, ages, and dies. Some live for billions of years, others for just a few million. When the light you see today left a star 500 light-years away, you're seeing that star as it was 500 years ago. If it exploded 200 years ago, you have no way of knowing yet. That light hasn't reached here. For you, on this night, that star still shines. You're looking at a ghost, a very real ghost, made of photons that exist and travelled and arrived, but the being that emitted them may have vanished centuries ago, millennia ago, entire geological eras ago. There is a widely spread myth that the stars we see are basically the same ones the ancient Greeks contemplated, immutable and eternal, fixed dots on an immobile vault. This is a very understandable confusion, because on the scale of a human life, or even the entire written history of humanity, the stars seem not to change. The sky Pythagoras saw was very similar to the one you are seeing. The constellations the Phoenician navigators used to cross the Mediterranean are recognizable on today's maps. But this is only because our lives are far too short to notice the change. Stars do change. They move, albeit very slowly from our point of view. They expand, they contract, they explode, they collapse, and at every moment somewhere in the observable cosmos, a star we saw yesterday may have ended its existence millennia ago, and the news simply hasn't reached us yet. The universe has no obligation to update us in real time. It operates at the speed of light, and for the cosmos that is the absolute maximum physics allows. For us existing in a minuscule bubble of space-time, this speed seems absurdly slow when applied to actual distances. Now, to understand why all of this works this way, we need to set the stage. To understand what a star truly is, not the little dot you see, but the immense physical object on the other side of that light. Because the light travelling to you is not random. It has an origin, a physics, a cause, and that cause reveals everything. A star is, in its most fundamental essence, a ball of gas, predominantly hydrogen, the simplest and most abundant element in the universe, with significant amounts of helium and traces of heavier elements scattered throughout the mixture. There is nothing solid in a star. There is no surface to land on. It is gas all the way through, from the centre to the edge, although the gas at the centre is under such extreme conditions that the word gas almost loses its usual meaning. The Sun, the star that keeps us alive and the only one we can study up close, has a diameter of about 1,390,000 kilometres. Inside it, more than 1 million Earth-sized planets lined up could fit. It is a sphere of incandescent plasma that has existed for about 4,600,000,000 years and is still in the middle age of its existence. But the Sun is an average star, a moderate-sized star with a long life and relatively calm behaviour. There are stars with diameters hundreds of times larger. The star VI Canis Majoris, for example, is so large that if placed in the Sun's position, its surface would extend beyond the orbit of Saturn. There are also stars much smaller than the Sun, cold, red, so economical in their burning that they can survive for trillions of years, far beyond the current age of the entire universe. Each of these stars emits light, and every ray of light they emit travels through the vacuum of space at the only speed physics allows for it, 300,000 kilometers per second. No shortcuts, no acceleration, no rest. Light does not age during the journey. It does not lose energy simply by the passage of time travelling, although it can be affected by the expansion of the universe in ways we will see later. It simply crosses the void, invisible, untouched, until something intercepts it. Sometimes that something is your retina. When this happens, when that photon that left a distant star travels for years or centuries or millennia through the vacuum and finally meets the back of your eye on a quiet night of observation, something happens that has no parallel in any other human experience. You close a circuit between yourself and a thing that may no longer exist. The photon was emitted, it travelled, it arrived, the link is real. But the origin may just be a memory of the cosmos. It is a form of time travel that requires no machine, that violates no laws of physics, that is available to anyone in any backyard on any clear night. You just need to look up. And this raises a question that becomes increasingly insistent as you absorb all of this. If light travels at this speed, if stars have a life that begins and ends, if what we see is always the past, then where, after all, does the energy come from that keeps a star shining for so long? What makes that light keep leaving, keep arriving, keep existing for billions of years before something finally runs out? Imagine you're trying to light a campfire with your bare hands. You take 2 sticks and start rubbing them together. At first, nothing happens. It seems the effort is useless, that the wood won't yield, that the heat you feel in your palms is just your own body complaining. But then something changes. A small wisp of smoke rises. A tiny ember appears, and suddenly that incandescent point transforms into flame, into heat, into visible light in the dark. What happened there was not creation, it was transformation. The energy that was sleeping in the molecular structure of the wood was released by friction and heat. It changed form, but it did not disappear. Now imagine that same principle operating on a scale that makes the campfire irrelevant by comparison. Imagine that instead of 2 sticks you have an amount of hydrogen so colossal that its gravity is able to compress the material at the center to densities and temperatures that the human mind cannot truly visualize. It is not an oven. It is not an explosion. It is a state of matter so extreme that the atoms themselves cannot maintain their identity. The electrons separate from the nuclei. The hydrogen becomes plasma, and the nuclei, naked and vulnerable, begin to collide with each other with a violence that breaks the barrier that would normally keep them apart. What happens at this moment is nuclear fusion. 4 hydrogen nuclei join together to form a helium nucleus, and in this process, a tiny fraction of mass disappears. It doesn't go anywhere you can see. It converts directly into energy, in amounts that undo any familiar proportion. This is where physics comes in with its most famous and most misunderstood phrase. Albert Einstein, working in the early 20th century on his studies of special relativity, arrived at a relationship that seemed too simple to be true. Energy equals mass times the speed of light squared. Written like this in running text, it seems almost trivial. But what this equation says is disturbing in its depth. It says that mass and energy are not different things. They are different forms of the same thing. They are 2 states of the same fundamental substance that the universe uses to build everything that exists. And what turns this from a mathematical curiosity into an observable reality is the number that appears in this relationship. The speed of light is enormous. Squared, it becomes a number that, if you tried to write it out in full characters, would take up more than half a page. This means that a microscopic amount of mass, when converted into energy, releases an amount of energy that goes beyond what any chemical reaction could produce. The sun loses, every second, an amount of mass equivalent to hundreds of millions of tons, and yet, after billions of years of doing this, it still has enough hydrogen to continue for another few billion years. The story of how we came to understand this goes through tortuous paths and minds that often did not live to see their ideas confirmed. In the late 19th century, there was a problem that disturbed the most serious physicists and geologists of the time. Geological estimates, based on the study of rock layers and the speed of erosive processes, suggested that the Earth was hundreds of millions of years old. Darwin, publishing his theory of evolution, needed an equally vast timescale for life to have time to diversify. But physicists had a problem. Lord Kelvin, one of the greatest physicists of the 19th century, calculated with all the rigour available at the time how long the sun could shine if its energy source were gravitational contraction. The idea was elegant. If the sun was slowly shrinking under its own gravity, this contraction would release gravitational energy that could be radiated as heat and light. Kelvin did the math and arrived at an answer. The sun could maintain its luminosity for a few tens of millions of years using only this mechanism. A long time for any human experience, but incompatible with what geologists and biologists needed. It was a genuine impasse. The instruments of two different sciences pointed in directions that could not both be correct. Someone was wrong, but no one knew who. Kelvin was so respected, his physics so rigorous, that many believed it was the geologists and biologists who needed to revise their estimates. The answer did not come from classical physics. It came from an unexpected source. In the early 20th century, the discovery of radioactivity by Henri Becquerel and later the work of Marie and Pierre Curie showed that there is a source of energy inside atoms that has no correspondence in conventional chemistry. Radioactive elements emit energy spontaneously, without combustion, without reaction with oxygen, without any process that classical physics could explain. It was as if matter itself held a reserve of energy that conventional thermodynamics had not noticed. This was the first sign that the interior of the atom hid something revolutionary. But the connection between radioactivity and the functioning of stars would still take decades to be established. It was necessary for Ernest Rutherford to map the structure of the atom, for James Chadwick to discover the neutron, for an entire generation of European and American physicists to build quantum mechanics before anyone could precisely formulate what happens inside a star. The decisive step came with Hans Bethe, a German physicist who had emigrated to the United States fleeing Nazism. In 1939, Bethe published a paper describing in detail the two main cycles of nuclear fusion that power stars. One of them, called the proton-proton chain, dominates in stars like the Sun. The other, called the CNO cycle, because it involves carbon, nitrogen and oxygen as catalysts, dominates in more massive and hotter stars. Bethe not only described the mechanisms, but calculated the reaction rates and demonstrated that the numbers matched the luminosity observed in stars. For the first time in human history, there was a physically complete and quantitatively verifiable explanation for sunlight. Bethe received the Nobel Prize in Physics decades later in recognition of this work, but understanding the fuel is not the same as understanding the balance, and it is the balance that transforms a collapsing ball of gas into a stable star capable of shining for billions of years. Here enters the fundamental imbalance that makes the theme work, and which is, paradoxically, a balance between two opposite imbalances. Think of it this way. You have an immense amount of gas. Gravity wants to compress this gas towards the center. The more gas, the stronger the gravity, the more intense the compression. If nothing resisted this, the entire star would collapse in a matter of hours, perhaps minutes, until it became something too dense to emit any light. But nuclear fusion resists. When the core of the star is compressed enough by gravity, the temperature rises to the point where fusion begins, and fusion generates energy. Energy generates pressure. Pressure pushes outward, so we have a cosmic tug of war. Gravity pushing inward, radiation pressure pushing outward, and as long as there is enough hydrogen to maintain fusion, these two arms balance each other in something astrophysicists call hydrostatic equilibrium. The star does not collapse. It does not explode. It just shines. It is a dynamic equilibrium, not a static one. If for some reason the fusion rate decreases, the pressure drops, gravity compresses the core a little more, the temperature rises, the fusion rate increases, the pressure returns. If the fusion rate increases too much, the pressure expands the core slightly, the temperature drops, fusion slows down. The star has a self-regulating mechanism built into the very physics that governs it, a cosmic thermostat that was not designed by anyone, and that emerged from the laws of nature as an inevitable consequence. This understanding changed not only astrophysics, but the way we think about stability in the universe. Complex and stable structures do not need an external architect. Sometimes two opposing processes meet and create, out of pure necessity, a territory of equilibrium that lasts longer than any force structure could. There is a law that silently governs all of this, and is rarely mentioned when talking about stars, but which is perhaps the most fundamental of all. It is the conservation of energy. It says that energy cannot be created or destroyed, only transformed from one form to another. The energy that reaches your eye in the form of visible light began as the energy contained in the mass of hydrogen nuclei that fused billions of years ago. It went through successive transformations inside the star, travelled through space as electromagnetic radiation, crossed the vacuum without losing its identity, and arrived. Nothing was created. Nothing was destroyed. Everything was just redistributed. Alongside this law, there is the second law of thermodynamics, which is less intuitive and more melancholic. It says that physical processes tend to follow a direction, that the universe moves from more ordered states to less ordered states. That entropy, which is a measure of disorder, tends to increase. A star is, from this perspective, a slow and grand process of increasing entropy. It consumes ordered hydrogen and produces helium, carbon, oxygen, progressively heavier and more mixed elements. It spreads energy through space in all directions, increasing the disorder of the universe while simultaneously maintaining, locally, an extraordinary order and regularity. And it is here that the process you have just understood begins to reveal a deeper layer, because what has been described so far is what happens inside a common, medium-sized star in its main phase of existence. But stars are not all the same. They are born with different masses, and the mass of a star determines everything. It determines the intensity of the gravitational field. It determines the temperature of the core. It determines the fusion rate. It determines how long it will last. It determines in the end how it will die. A star with a mass close to that of the Sun will burn slowly for an amount of time that escapes comprehension. But a star with 10, 20, 50 times the mass of the Sun will burn with such greater intensity that its hydrogen stock runs out in a fraction of that time. And when this happens, the self-regulation that maintained the balance begins to fail. The pressure decreases. Gravity begins to win the tug of war. What happens when this imbalance we described, this balance between gravity and pressure, begins to repeat itself not just once, but in stars of radically different masses, at radically different temperatures, over radically different timescales, in every corner of the galaxy, in every observable galaxy in the universe, for billions of years, simultaneously, in parallel, in cascade? What happens is that the entire universe becomes an organism, not in the biological sense, not as a poetic metaphor someone invented to simplify what is complicated, but in the most rigorous structural sense of the word, parts that do not know each other, that have never touched, that are separated by distances that take millions of years for light to cross, behave in coordinated ways. They produce patterns, they create hierarchies, they organize themselves into architectures that no individual component chose, that no one designed, that emerged from rules so simple they fit into a few equations, but whose results are so complex that it has taken us centuries to begin reading them. The first thing that arises when you look beyond an individual star and start observing stellar populations is that they are not distributed randomly. This perception seems obvious today, but for most of human history it was not. The night sky seemed a patternless pattern, a scattering of dots that the human imagination organized into constellations because the mind needs order even when nature does not visibly offer it. It took the development of optical instruments, systematic catalogues, statistical mathematics, and above all a willingness to ask not just what stars are but where they are and why they are there, for us to begin to see the underlying structure. In the 18th century, William Herschel spent decades counting stars in different directions of the sky, trying to map the shape of the Milky Way by the most direct method possible. If there are more stars in one direction, the system extends further in that direction. His model was wrong in fundamental proportions, because he did not yet know that interstellar dust blocks light and distorts any count, but the instinct was right. The galaxy has a shape. It is not an amorphous cloud. It is a structure, and this structure imposes conditions on the birth, life, and death of every star within it. The shape we recognize today is that of a spiral disk, with a denser central bulge, arms that coil outward in a pattern that repeats with variations in galaxies across the observable universe. These spiral arms are not solid structures that rotate like fan blades. They are density waves, regions where matter periodically compresses as the disk rotates. An imperfect but useful analogy is that of a traffic jam on a circular highway. The cars move forward, but the point of congestion can remain relatively stationary, or move at a different speed than the cars themselves. Stars pass through the spiral arms of the galaxy along their orbits, and as they pass through regions of higher density, the gas clouds accompanying them undergo compression, and this compression triggers waves of star formation. This means that the spiral arms are privileged regions of stellar birth. The young, hot, massive, and blue stars that burn most intensely are concentrated in the arms because they were born there and have not yet had time to disperse. The older, more slowly evolving stars are distributed more evenly throughout the disk. The galaxy, when you look at it in ultraviolet light that reveals the youngest and hottest stars, looks completely different than when you look at it in infrared light that reveals the older populations. Two portraits of the same structure that look like portraits of different things, because the history of star formation wrote itself in different ways at different wavelengths. This age gradient has a consequence that takes time to appreciate in its depth. The place where a star is born within the galaxy determines what environment it will exist in, what kind of matter it will find around it, what explosions from neighbours might disturb its natal cloud, or conversely compress other clouds and trigger new stellar generations. Stars are not islands. They are participants in a galactic ecology where each generation modifies the environment for the next. The matter that makes up stars today is, to a large extent, material that has gone through previous cycles of stellar formation and destruction. The early universe produced hydrogen and helium in abundance, and traces of lithium, and essentially nothing else. Every heavier element we find today, in planets, in oceans, in living organisms, was forged in the interior of stars and scattered through space when those stars died. A star born today in our galaxy is born from a mixture that contains the waste of previous generations, and this means it has at its disposal, from the very beginning, elements that modify its internal physics in subtle but important ways. The carbon and oxygen present in minimal amounts in a current galactic gas cloud affect how heat escapes during the cloud's collapse, which affects the size of the fragments that form, which affects the mass distribution of the stars that are born. This is where something astronomers call the initial mass function begins to emerge, one of the most remarkable relationships the universe manifests. When a gas cloud collapses and fragments to form a star cluster, the fragments are not all the same size. There are far more small fragments than large ones. The resulting mass distribution follows a statistical pattern that repeats, with variations, in star clusters throughout the galaxy, in other galaxies, at different epochs of the universe. Edwin Salperes mathematically described this distribution in the mid-20th century, and what his equation reveals is astonishing. The universe has a statistical preference for the mass of the stars it produces. It is not a preference in the sense of a conscious choice. It is the inevitable result of how the physics of gravitational collapse, radiation pressure, cooling by the emission of electrons and atoms, and gas turbulence combine to fragment a cloud. Massive stars, those that burn most intensely and die earliest, are rare. Intermediate mass stars like the Sun are more common. Low-mass stars, which burn so slowly they will last longer than the current age of the universe, are the most numerous of all. The galaxy is numerically dominated by stars we can barely see, faint red dwarfs that exist in silence for unimaginable eras. This asymmetry has consequences for what the night sky reveals. The stars we see with the naked eye are, in the overwhelming majority, rare objects. Stars that are bright because they are massive, or because they are close, or because they are in a late stage of evolution where they have expanded to gigantic dimensions. The typical star of the galaxy is invisible to us without instruments. The universe we perceive directly is a profoundly biased sample of the real universe. When Cecilia Payne-Gaposchkin demonstrated in the 1920s that stars are composed predominantly of hydrogen and helium, and not of a mixture similar to Earth's as was assumed, she opened the door to understanding that the chemical composition of a star is not a peripheral detail, but a central variable that governs all its physics. And when it was realized that this composition varies systematically with position in a galaxy, with the age of the star, with the generation to which it belongs, it became clear that we were looking at a chemical evolution of the entire universe, a chemical narrative unfolding on a cosmic scale over billions of years. In the galactic disk, close to the center where stellar generations succeed each other more rapidly, stars are on average richer in heavy elements than the stars of the galactic halo, the ancient populations that formed when the galaxy had little more than primordial gas. This difference in composition is readable in the light each star emits. The spectra of halo stars are simpler, closer to the purity of hydrogen and helium. The spectra of young stars in the disk are more elaborate, crossed by signatures of iron, oxygen, carbon, magnesium, silicon, the entire periodic table written in light. Reading stellar spectra is one of the most profound activities human science has ever developed. When Josef von Fraunhofer catalogued the dark lines in the solar spectrum in the early 19th century, he did not know what he was seeing. Decades later, when Gustav Kirchhoff and Robert Bunsen established that each element absorbs and emits light at specific wavelengths, it became possible to identify the chemical composition of objects at immense distances simply by analyzing their light. A galaxy hundreds of millions of light years away delivers its chemical composition in a photographic exposure, if you know how to read it. And what these spectra reveal, when you begin to compare them systematically, is that the universe is chemically evolving in real time, that the composition of the cosmos is different today than it was 5 billion years ago, different still than it was 10 billion years ago, different than it was when the first helium atom was formed after the initial moment of expansion. Each generation of stars delivers to the universe a legacy of elements that did not exist before, and this legacy accumulates, concentrates, and distributes itself through the clouds that will form the next generation. The geometric distribution of these stellar populations within a galaxy is also not neutral. The thin disk where most young stars reside has a much smaller thickness than its diameter. Stars formed in the thin disk with random peculiar velocities, perturbed by gravitational encounters with massive clouds or density waves, can migrate to the thick disk over eras of time. The thick disk has an older population, more dispersed vertically, with a chemical composition intermediate between the thin disk and the halo. The galaxy is not a discrete structure in two parts, but a continuous gradient of populations that record the history of galactic formation in their spatial distribution. When we move even further away and look not at a single galaxy, but at groups of galaxies, at clusters, at superclusters, at the filaments and voids that make up the large-scale structure of the universe, we find the same logic operating again on a larger scale. Galaxies are not distributed randomly through space. They are organized into structures that look like networks of bubbles, where galaxies concentrate in the filaments and intersections, and the vast interior spaces of the bubbles, the great voids, are almost completely devoid of bright galaxies. This large-scale structure emerged from the same tiny quantum fluctuations that existed in the first instance of the universe, amplified by gravity over billions of years, until it became the cosmic tapestry we observe. And in this tapestry, the rate of star formation, the mass distribution of stars, the frequency of supernova explosions, all of this varies from region to region in a way that reflects the history of each part of the cosmos. The filaments are rich in spiral galaxies with active star formation. The dense centers of large clusters tend to be dominated by ancient elliptical galaxies, where star formation ceased long ago. Consumed in intense explosions in remote epochs, the voids have their own galaxies, but they are smaller, more isolated galaxies, with quieter star formation histories. The position of a galaxy in the cosmic tapestry shapes its stellar history just as much as the total mass of gas it contains. All this architecture, from the collapse of an individual molecular cloud to the arrangement of superclusters in the observable universe, obeys principles that are essentially the same. Gravity compresses, pressure resists, instability produces structure, structure feeds back into the process that generated it. But there is something missing in this description, something that when considered in its absence makes the picture much simpler and much less like the universe that actually exists. The patterns we described, this richness of populations, ages, compositions, and distributions, would be more uniform, more predictable, more well-behaved, if there were not an ingredient that introduces into the system a perturbation of disproportionately greater amplitude than its local size suggests, a perturbation that propagates beyond its immediate origins and rewrites the conditions of the surrounding environment over distances and durations we're only just beginning to map. That ingredient is radiation. Not radiation as a vague concept that evokes fear or mystery, but as a precise physical phenomenon, energy that propagates through space without needing a material medium to do so, that travels at the highest speed nature allows, that crosses the vacuum with the same ease with which it crosses eras of cosmic time. Radiation is the universal messenger of the universe, and it is also, in ways that go far beyond the role of mere messenger, the agent that perturbs, that heats, that ionizes, that expels, that compresses, that rewrites the conditions of the interstellar gas on scales that no other individual process can rival. What makes radiation such a disproportionate amplifier is precisely what seems to be its most banal characteristic. It travels in a straight line at a constant speed, expanding spherically from its source. A massive star at the center of a molecular cloud does not need to physically touch the gas surrounding it to transform it completely. It simply exists, shines, and the photons it emits carry enough energy to strip electrons from hydrogen atoms at distances of tens of light years. This process has a technical name, photoionization, and its local consequences are a region of ionized hydrogen that astronomers call an H2 region, a bubble of hot, bright plasma that can have a diameter equivalent to hundreds of times the distance between the Sun and the nearest star to us. But the amplifying effect is not only in the scale of ionization. it is in the dynamics it triggers. When gas is ionized by intense radiation, its temperature rises dramatically. A cold molecular gas in a typical interstellar cloud is at temperatures of just a few tens of degrees above absolute zero. An H2 region created by an O-type star, the most massive and luminous stellar class that exists, can be at temperatures of 10,000 degrees. This temperature difference creates a pressure difference. The hot region expands against the cold gas around it, compressing the boundary where the two meet into a dense layer called an ionization front. And this compression, paradoxically produced by light, can be exactly the missing trigger for new gravitational instabilities to settle in the compressed gas, leading to the collapse of new cores and the birth of new stars. This mechanism is called ionization-stimulated star formation, or more poetically, collect and collapse star formation, because the ionization front literally sweeps the gas ahead of it and piles it into denser configurations than those that existed before. A single massive star can, through this process, be responsible for the birth of dozens or hundreds of lower mass stars in the surrounding regions. It does not create them directly. It creates the conditions for gravity to do its job more efficiently. Radiation is the catalyst, and like any good catalyst, its presence completely transforms the final product without appearing directly in it. There is yet another mechanism by which radiation amplifies its influence beyond ionization: radiation pressure. Photons have no rest mass, but they have momentum. When a photon is absorbed by an atom or a dust grain, it transfers to that atom or grain an amount of momentum that is minuscule for a single photon, but which, multiplied by the astronomical numbers of photons emitted by a massive star every second, produces a real and measurable force. In sufficiently luminous stars, this radiation pressure can exceed the gas pressure and drive stellar winds at speeds of thousands of kilometers per second, ejecting material from the star into the surrounding space and creating bubbles of rarefied gas that expand for light years around the star over its lifetime. The visible manifestations of these interactions between radiation and matter are some of the most beautiful structures the cosmos produces. Emission nebulae like the Orion Nebula that anyone with reasonably good binoculars can see as a softly luminous smudge below the belt of that constellation are H2 regions illuminated from within by their own young stars. The characteristic red glow we record in long exposure photographs comes from hydrogen atoms capturing free electrons and, in doing so, emitting photons at a specific wavelength called Balmer alpha, corresponding to an electronic transition between well-defined energy levels. Every photograph of an emission nebula is literally a map of where radiation is interacting with gas, where the boundaries are, where matter is being compressed, and where it is being dispersed. Reflection. Nebulae are a different but equally revealing phenomenon. Instead of emitting their own light through ionization, they simply reflect the light of nearby stars using the dust grains they contain. This dust preferentially reflects blue wavelengths, by the same principle that makes the Earth's sky blue, Rayleigh scattering, where small particles deflect short wavelength light much more efficiently than long wavelength light. The result is a bluish, ethereal haze surrounding certain stars, a silent testament that the region around them is still full of material that has not been ionized or dispersed, only obliquely illuminated by the stellar neighborhood. There are also dark nebulae, which are in a sense the opposite manifestation, regions of gas and dust so dense that the light from stars behind them cannot penetrate them, creating silhouettes of darkness cut out against the diffuse background glow. The Horsehead Nebula in Orion is perhaps the most famous example, a pillar of dense gas rising from an even denser, larger region, its shape sculpted by the winds and radiation of surrounding stars. These dark nebulae are often stellar nurseries in the early stages of collapse, regions where the density has already passed the threshold of Jeans instability, but where the formation process has not yet begun to illuminate the darkness from within. there is a type of structure that brings all these manifestations together in a single image and illustrates with unusual clarity the mechanism of amplification by radiation, the so-called Bok globules. These are compact, roughly spherical condensations of gas and dust, usually 1 to 5 light-years in diameter and with masses of a few suns, that appear as isolated dark spots projected against the glow of emission nebulae. They were named in honour of the Dutch-American astronomer Bart Bok, who identified them and proposed in the 1940s that they could be sites of star formation. Decades later, infrared observations confirmed that many of them do indeed contain young stars inside. Exactly as Bok had predicted, they are the simplest and most understandable units of star formation, and at the same time they are structures that exist only because of the surrounding radiation. Without the pressure of the ionization front pushing the cold gas, many of these globules would not have reached the density necessary to collapse. If you have ever looked at a photograph of the Pillars of Creation Nebula, that iconic image captured by the Hubble Space Telescope, you have seen this process in action. Those pillars of gas and dust rising like fingers pointing into the darkness are not static structures. They are what remains of a more extensive molecular cloud that is being eroded by the radiation of young, massive stars around them. The tips of the pillars, denser and more capable of resisting erosion for a longer time, are often sites where new stars are beginning to form, driven by the very pressure that is destroying the larger structure around them. It is an image of simultaneous destruction and creation, mediated entirely by radiation as the common agent. The human experience with these manifestations does not need a space telescope to begin to exist. When you look at the sky on a clear night and see the Milky Way as a band of diffuse light, you are seeing the sum of billions of stars and all the interstellar haze that surrounds them, a texture that is not uniform precisely because the radiation from the most massive stars has already sculpted the gas into structures with varied densities and distributions. The brightest regions of the galactic band correspond to parts of the disk where star formation is most active, where emission nebulae are illuminated from within, where ionized gas glows at the wavelengths our eyes are sensitive to. The darker regions within the band are not absences of stars but the presence of dark clouds, those absorption nebulae that block the light of more distant stars exactly as Bok globules block the glow of surrounding emission nebulae. There is a curious and almost poetic symmetry in the fact that the same process that creates the conditions for the birth of stars is also the process that eventually destroys those same conditions. While a massive star lives, its radiation ionizes, heats, compresses, and stimulates formation around it. When it dies in a supernova, the explosion sends a shock wave that can fragment the remaining molecular clouds in ways much more violent than gradual ionization ever could. And after the explosion, the supernova remnant nebula, a bubble of gas expanding at speeds of several thousands of kilometers per second, can collide with adjacent molecular clouds and compress them in a single pulse of mechanical energy that triggers another generation of star formation. Radiation, therefore, is not just an amplifier of existing instabilities. It is an agent that creates instability, propagates it, resolves it, and restarts the cycle in new regions. This cycle has a quality that could be called resonant. Each generation of massive stars creates the conditions for the next generation, and this pattern perpetuates itself over hundreds of millions of years in a dance that sweeps through the galactic disk following the spiral arms like density waves that compress the interstellar gas and provoke bursts of star formation along their passage. The spiral arms are not solid structures that rotate with the galaxy as a whole. They are density patterns like waves on a lake that propagate through the disk more slowly than the individual stars around them. As gas enters a spiral arm, it is compressed, and this compression added to the radiation from the massive stars that the previous burst of star formation already created in the arm can be enough to keep the cycle active indefinitely. What emerges from this picture is an image of equilibrium that seems at first glance quite robust. The galaxy has mechanisms that feed back into star formation, that distribute the energy of the most violent processes throughout the most extensive structure, that convert gas into stars at a rate that has remained relatively stable over billions of years. The long-lived stars, the yellow and orange and red dwarfs, exist in sufficient numbers to ensure that the galaxy continues to shine for eras the mind cannot fully embrace. The gas reservoirs, although gradually being consumed, still contain enough material to sustain formation for a time comparable to the current age of the universe. But this equilibrium, no matter how stable it may seem when viewed on a cosmic scale, rests on conditions that are surprisingly specific. The star formation rate in a galaxy like the Milky Way depends on a delicate relationship between the influx of fresh gas from the galactic surroundings, the efficiency with which that gas converts into stars, and the violence with which the most massive stars destroy the remaining material before it can be used. Alter any of these parameters sufficiently, and the equilibrium breaks in ways that can be irreversible. Galaxies that have experienced sufficiently severe perturbations, collisions with other galaxies, starburst episodes so intense they exhausted the available gas in a few billion years, or the presence of an active galactic nucleus that heated the surrounding gas beyond the point of collapse, can lose their ability to form new stars completely and become barren, silent, filled only with the old stars that survived the turmoil. Galaxies that have become barren, silent, filled only with aging stars that survived the turmoil. This image of forced quietude is the backdrop against which the most dramatic phenomena of the cosmos gain their true weight. Because the silence that falls over an exhausted galaxy does not arrive gently. It is the result of a sequence of events that, once triggered, follows its path with an implacable internal logic, breaking thresholds that can never be restored, transforming what was once a living, expanding system into something that merely consumes the legacy of what was. To understand how a star can leave its calm behavior and enter a state of catastrophic intensity, one must first recognize that every star is a negotiation between forces. For most of its existence, it maintains an implicit agreement with physics. The gravity collapsing the gas toward the core is counterbalanced by the pressure of the radiation and hot plasma generated by nuclear fusion. This equilibrium is not passive. It is a continuous process, a dance where any deviation generates a corrective response. If the internal pressure drops, gravity squeezes the core a little more, which accelerates fusion, which in turn restores the pressure. If the pressure rises too much, the star expands slightly, which cools and dilutes the core, slowing down fusion. This feedback mechanism keeps billions of stars in equilibrium for billions of years, and it is precisely why the sun appears so reliable in the morning sky. But there is a threshold beyond which this correction mechanism fails. When the hydrogen in the core of a massive star begins to run out, the star initiates a series of nuclear transitions, burning helium, then carbon, then neon, then oxygen, each cycle faster than the last, each fusion layer closer to the surface, building a cascading structure of concentric layers like those of an onion. At the center of this onion, silicon finally converts into iron, and this is where the agreement between forces reaches its absolute limit. Iron is the most stable element in the universe in a nuclear sense. It does not release energy when fused, it consumes it. The moment an iron core reaches a critical mass, fusion stops completely, and the radiation pressure that sustained the entire star vanishes in a fraction of a second. The core collapses on itself at a speed that defies intuition, contracting from a volume comparable to Earth's to a sphere with a radius of just a few kilometers in less than a second. This implosion releases an amount of energy that far exceeds the total luminosity of the sun over its entire life, and the result is a supernova. A supernova is not simply a large explosion. It is a threshold crossed irreversibly, a breaking point where the physics of the previous state ceases to apply, and a completely new reality emerges from the wreckage. The shock wave propagating outward through the stellar material surrounding the collapsing core travels at a significant fraction of the speed of light, compressing, heating, and ionizing everything it encounters. Elements that took millions of years to be synthesized in the fusion layers are catapulted into the interstellar medium in a matter of days. Calcium, iron, nickel, gold, platinum, uranium, all these elements that make up planets and living beings and future stars are forged and dispersed by this single violent event. The supernova is not just the death of a star, it is the condition of possibility for everything that comes after. What remains at the center after the collapse depends on the original mass of the star. For moderately high-mass stars, the core survives as a neutron star, an object of inconceivable density where electrons have been forced into protons, neutralizing them and creating a state of matter that does not exist anywhere else on the macroscopic scale of the cosmos. A neutron star with the mass equivalent to tens of trillions of tons concentrated in a volume roughly the diameter of a medium-sized city spins hundreds of times per second just after its formation, emitting extremely narrow beams of electromagnetic radiation from its magnetic poles. When these sweeping beams point toward Earth with each rotation, we observe a pulsar, a signal so regular that the first astronomers who detected it doubted for a few moments that it was natural. This mechanical regularity in an object forged from absolute chaos is one of the most disconcerting contrasts the universe offers. For even more massive stars, not even the degeneracy pressure of neutrons is enough to resist the gravity of the collapsing core. In these cases, the collapse continues without any mechanism to stop it, until all the mass is compressed into a point of singular density called a singularity, enveloped by a region of space from which not even light can escape, a black hole. A black hole is not an object in the conventional sense. It is a region of space where the curvature of space-time geometry has reached such a degree that all possible trajectories, including those followed by light, point inward. From the point of view of a distant observer, an object falling toward a black hole appears to move slower and slower as it approaches the event horizon, freezing there due to an effect of gravitational time dilation, and eventually disappearing, erased by the increasing redshift that shifts its radiation out of the detectable range. It is a slow-motion disappearance that, from the point of view of the falling object, happens in finite time without any perceptible boundary. Humanity learned to observe these phenomena through paths that would have been unthinkable for astronomers a few centuries ago. Optical telescopes capture the light curve of a supernova while it shines for weeks or months, sometimes outshining the entire host galaxy in luminosity. Neutrino detectors buried kilometers below the Earth's surface, built to capture particles that pass through solid matter with almost no interaction, can record the pulse of neutrinos emitted by the stellar core collapse before the light from the explosion has even left the star's envelope, because neutrinos escape through the overlying layer of material much more easily than photons. The supernova, called 1987A, in the Large Magellanic Cloud, provided the first coincident detection of neutrinos and optical light, confirming the theory of core collapse with a precision that decades of previous observations had not achieved. The detection of gravitational waves inaugurated an entirely new era in the observation of these boundary events. When two black holes or two neutron stars orbit each other in an ever-tightening spiral and finally collide, they perturb the very geometry of space-time around them, sending ripples that propagate at the speed of light in all directions. These ripples, called gravitational waves, alternately compress and stretch the space they pass through by absolutely minuscule amounts, a fraction of the diameter of a proton, over a distance equivalent to a stretch of a few kilometers. Detecting this requires precision instruments that rank among the most sophisticated our civilization has ever built. interferometers with arms kilometers long, where lasers measure length variations with precision, surpassing any other measurement ever made. When two black holes with masses of tens of solar masses each collide at distances of billions of light years, terrestrial observatories feel the echo in space-time of an event that occurred when multicellular life had barely emerged on this planet. While you rest, somewhere in the galaxy or beyond it, a star is now crossing the threshold. There is no way to know precisely where or when, because the light that would inform us about it is still in transit, traversing space at a finite speed while the event has already consummated its irreversibility. In some distant galaxy, an iron core is collapsing right now, and the energy of this implosion is being distributed through the wreckage of a sun that burned for millions of years. Elsewhere, two stellar remnants that orbited each other for eons finally touch, and the gravitational wave generated by this merger is now propagating in all directions, eventually reaching the instruments humanity built to hear the universe vibrate. These dynamic structures, the pulsars spinning with clockwork precision, the debris clouds expanding and cooling into nebulous mists that will in turn feed new generations of stars, the black holes silently devouring the material orbiting around them, are all the persistent generated in intense mode, the scars and legacies of crossed thresholds. The mist that remains after a supernova is called a supernova remnant, and it is not static. On the contrary, it is an extraordinarily rich plasma physics environment, where the expanding shockwave continues to accelerate particles to energies that no human accelerator has yet reproduced. These particles, called cosmic rays, permeate the entire galaxy, and some of the most energetic among them reach Earth and are detected by networks of detectors spread over vast areas of terrain or by underground experiments. They carry information about the processes that generated them, about the galactic magnetic fields that deflected them on their path, about the very chemical composition of the objects from which they emerged. Each cosmic ray is, in this sense, a message from a past event, from a threshold crossed at some point in galactic history, arriving at the detector now via a trajectory that physics does not allow to trace precisely back to its origin. The elements dispersed by these dramatic events do not remain isolated in the interstellar medium. They mix with the primordial gas, enriching its chemical composition, making it progressively more metallic in astronomers' jargon, where any element heavier than helium is called a metal, regardless of its chemical properties. This gradual enrichment changes the properties of the stars that form from this gas, altering their opacity, their surface temperature, their luminosity, the type of planets that condense around them, and, by extension, the conditions under which life may or may not emerge. The dramatic phenomena that end the lives of individual stars do not happen in isolation from the rest of the cosmos. They modify the environment from which the cosmos will continue to build structures, and the effects of these modifications propagate forward in time in ways we're only just beginning to map with any depth. This enriched gas, bearing all the chemical memory of previous stellar generations, does not float passively through space, like an inert substance awaiting a destiny. It actively participates in a dialogue that has no identifiable beginning or predictable end, a dialogue between the matter that tends to contract and the forces that resist that contraction. The most intimate partner in this entire process is gravity, not as an external force acting on the gas from the outside in, but as an intrinsic property of matter itself, a tendency that emerges from within every concentration of mass and never ceases to work in silence, patiently accumulating the potential necessary to transform diffuse clouds into resplendent suns. Gravity and interstellar gas form, together the main dance partners of the cosmos, and every star that has ever existed or will ever exist is a product of this choreography that repeats itself with infinite variations over time. What makes this pair so extraordinarily productive is precisely the nature of the exchanges established between them. When gas contracts under gravitational influence, it heats up. When it heats up enough, it initiates nuclear reactions. When nuclear reactions produce enough energy, the resulting radiation pressure resists gravity, creating a temporary equilibrium we call a stable star. But this equilibrium is not a state of rest. It is a state of active tension, a continuous negotiation between forces pulling inward and forces pushing outward. While this negotiation holds, the star shines. When the fuel runs out and the radiation pressure decreases, gravity regains its advantage and the collapse begins again, leading to new stages of fusion, new structural crises, and eventually the kind of end that the weight of the star determines. This entire cycle is a form of energy exchange between gravity and matter, and each cycle leaves the universe slightly different than it was before. The feedback cycles that emerge from this interaction have an elegance that defies simple description. Consider what astronomers call stellar feedback on star formation. When a generation of massive stars forms in a giant molecular cloud, the youngest and hottest stars emit intense ultraviolet radiation that ionizes the surrounding gas, creating bubbles of hot plasma that expand into the cloud. This expansion compresses the outer layers of the cloud, potentially both triggering the formation of new stars at the compressed edges and dispersing the available gas and suppressing star formation in other regions. The same stellar generation that forms can, therefore, both stimulate and inhibit the formation of subsequent generations, depending on the local geometry, the density of the gas, the speed of stellar winds, and dozens of other parameters that vary from region to region within the galaxy itself. Detailed observations of nearby star-forming regions, such as the Orion Nebula, about 1,300 light-years away, reveal this dynamic in action with a wealth of detail that no theoretical simulation can yet fully reproduce. There, young, hot stars ionize the surrounding gas, creating Bock globules, which are dense, dark condensations of gas that seem to resist ionization and will eventually collapse to form new stars. The same radiation that threatens to destroy these globules also compresses them slightly, accelerating their collapse. The fire that could consume the seed is also what makes it germinate with urgency. This kind of feedback, simultaneously destructive and creative, operates on timescales of a few tens of millions of years within a single star-forming region, and is repeated in countless locations throughout the galaxy at different moments in its historical development. In the short term, which for astronomy can mean a few hundred or a few thousand years, what we observe are discrete events: a star exploding here, a planetary nebula expanding there, a pulsar gradually slowing down as it radiates its rotational energy into the surrounding medium. These events seem isolated when we contemplate them on a human scale, because our entire lives represent an insignificant fraction of the time, separating one event from another. A human being who dedicated their entire life to studying a specific region of the sky would not live to see anything more than a snapshot of processes unfolding on timescales incompatible with direct human experience. What we call observational astronomy is, to a large extent, the art of inferring dynamics from snapshots, of reconstructing movies from isolated frames. On timescales of a few million years, patterns begin to emerge more clearly. A galaxy like the Milky Way goes through cycles of star formation that intensify when it interacts gravitationally with smaller galaxies around it, or when the distribution of dark matter in its halo changes enough to alter the flow of gas toward the center. Computer simulations based on observational data of galaxies at different stages of their development suggest that the rate of new star formation in the Milky Way was much higher in the past, perhaps 10 times higher than it is today, and that we are living in an era of relative stellar tranquility. The stars being born today are children of a more mature universe, formed from gas already deeply enriched by countless previous generations, with chemical compositions that allow for the existence of rocky planets rich in heavy elements and, presumably, conditions favourable to life as we know it. In billions of years, the scenario changes in ways that begin to challenge our intuition. The Sun, like all stars of its mass, will eventually exhaust the hydrogen in its core and expand into a red giant, probably engulfing the orbits of the inner planets and certainly irreversibly altering any condition that currently supports life on Earth. This event, although certain in its general characteristics, is about 5 billion years in the future, a time interval so vast that it is practically impossible for the human mind to comprehend it with any real sense of scale. For a frame of reference, the entire universe is about 13.8 billion years old, and the Earth formed about 4.5 billion years ago. Complex multicellular life has existed for less than 600 million years. 5 billion years from now is more than all the time elapsed since the formation of the planet where this conversation is taking place. Beyond billions of years, the universe moves toward a state that physicists describe with words like darkness and silence, not as poetic metaphors but as technical descriptions of a thermodynamic state. The lightest stars, those with masses less than about 80% of the solar mass, have lives so long that none of them have died of natural causes since the beginning of the universe. But eventually even these stars will consume their fuel. The gas available for the formation of new stars will gradually be incorporated into stars, planets, white dwarfs, neutron stars, and black holes. The star formation rate will continue to decrease. On timescales of trillions of years, the universe will become progressively darker, its last focal points of light going out one by one at increasingly spaced intervals, like candles in a cathedral that no one ever revisits. This long-term trajectory raises questions about the limits of prediction. How much can we really know about the future of such a complex system? Sensitivity to initial conditions is a concept that gained popular recognition through chaos theory. But in astrophysics it takes specific and often surprising forms. A tiny difference in the mass of a star at the moment of its formation can determine whether it ends its life as a relatively serene white dwarf or as a supernova that seeds hundreds of light-years of space with heavy elements. A difference in the initial density of a molecular cloud can determine whether it collapses into a single massive star or a cluster of smaller stars, with completely different consequences for the local chemistry of the interstellar medium over the next tens of millions of years. There are also limits that are not the product of sensitivity to initial conditions, but of deeper fundamental uncertainties. We do not know with sufficient precision how turbulence in the interstellar gas develops on small scales. We do not fully understand how magnetic fields, which permeate the galaxy in complex and variable configurations, interact with the gas during gravitational collapse. We do not have a complete theory of how the core of a neutron star forms during the milliseconds of a supernova explosion, and this ignorance prevents us from confidently predicting which supernova produce neutron stars and which produce black holes. Each of these blind spots represents not just a technical problem awaiting a solution, but a window into the genuine complexity of a universe that was not built to be completely legible. And yet, within all these limits, within all these uncertainties, there is something that works consistently and wonderfully. The same physical laws that govern a candle flame in the laboratory govern nuclear fusion in the core of a star 200 light-years away. The same thermodynamic principles that describe the behavior of a gas in a pressure chamber describe the behavior of interstellar gas on a galactic scale. The spectrum of light a star emits carries a precise chemical signature that we can decode using the same atomic principles developed in terrestrial laboratories. This universality of physical laws is not a small thing. It is the most profound and surprising fact science has discovered about the nature of the cosmos, more surprising than any individual phenomenon, more profound than any specific experimental result. It is in this universality that a particular beauty resides, a beauty that is not the beauty of ornamentation or formal perfection, but the beauty of something that is at the same time comprehensible and inexhaustible. Comprehensible because the tools we developed, mathematics, physics, chemistry, systematic observation, actually work. They really tell us something true about how the universe operates. Inexhaustible because with every answer obtained, a set of new, deeper, more subtle, more difficult to precisely formulate questions emerges. We learned that stars explode and enrich the cosmos. We spent decades trying to understand exactly how supernovae work and discovered that the process is much more complicated than we suspected. We learned that enriched gas forms new generations of stars. We tried to model this formation and discovered that turbulence, magnetic fields, and the feedback from the young stars themselves create a complexity we have not yet fully mastered. There is a moment that some scientists describe, in private conversations, away from the technical language of scientific papers, as the moment they realize they are facing something that completely exceeds the capacity of any individual mind to contain. It is not an experience of defeat. It is almost the opposite. It is the realization that the object of study is genuinely larger than the instrument studying it, that reality has a depth that human curiosity will never be able to exhaust, not for lack of intelligence or effort, but because the depth is real and has no visible bottom. This realization does not paralyze, it invites. It transforms scientific work from a task with a beginning and an end into something more like a practice, something done not to finish, but because the doing itself is where the meaning resides. All this fabric of interactions, of feedback cycles, of time scales stretching from the millisecond to the trillion years, of universal laws expressed in unrepeatable local phenomena, points in a direction we have not yet fully articulated. Behind all this elaboration, all this richness of processes and structures and histories, there is something simpler than all of it. Not simple in the sense of easy, but simple in the sense of fundamental, irreducible, anterior to all the complexity that emerges from it. Behind all this elaboration, all this richness of processes and structures and histories, there is something simpler than all of it. Not simple in the sense of easy, but simple in the sense of fundamental, irreducible, anterior to all the complexity that emerges from it. And when we reach this deepest place, we realize that the question of why we see stars that no longer exist is not a question about illusion or deception. It is a question about the nature of time, about the structure of reality, about what it means to exist in a universe where information travels at a finite speed through a space that is also expanding, that also has a history, that also emerged from an initial state of unimaginable density, and is moving toward a future of progressive silence. The feedback that sustains this vision begins in the very atoms that form the stars we see. When a massive star ends its life in a supernova, it does not just disappear. It scatters into interstellar space all the elements it forged in its core over millions of years, carbon and oxygen and iron and silicon and dozens of other elements that did not previously exist in that corner of the galaxy. This dispersion is the beginning of a cycle that feeds back on itself in extraordinary ways. The molecular clouds that will receive these elements will be enriched in metals, as astronomers call any element heavier than helium. Second and third generation stars born from these clouds will have different compositions than the first stars of the universe, and around these richer stars rocky planets may form, worlds with enough silicon and iron and carbon to build solid surfaces, oceans, complex atmospheres, and perhaps forms of chemistry that will one day look at the sky and wonder where they came from. This is the most vast feedback cycle we can contemplate. The death of a star fertilizes space for the birth of others, and each generation inherits the chemical complexity accumulated by all previous generations. The light we see from ancient stars is not just a signal of their past existence. It is also the record of a moment in this cycle, a snapshot of a generation of stars that was building the ingredients that would one day allow eyes and minds to exist to contemplate them. There is something profoundly circular about this, not in the sense of a logic spinning falsely, but in the sense of a process that sustains and deepens itself over time. The molecular dimension of this process is equally dazzling. Each photon of light travelling from the core of a star to its surface takes a tortuous path that can take tens of thousands of years, scattered and absorbed and re-emitted millions of times before finally escaping into space. The photon that eventually reaches us after millennia of travel through the interstellar vacuum has already traversed inside the star a path that tangles with the internal history of that sun. When it finally crosses our atmosphere and reaches the retina or the detector of a telescope, it brings with it not only information about the star's surface temperature, but traces of processes that occurred in its core long before the light escaped from there. The spectrum of this light, when analysed with sufficient precision, reveals the chemical composition of the star with a wealth of detail that continues to surprise spectroscopists. Each element absorbs and emits light at very specific frequencies, like a fingerprint that cannot be forged. When we see the dark lines in the spectrum of a distant star, we're reading the list of elements that existed in that star's atmosphere at the moment that light left. We are doing chemistry at a distance through time, using as a tool only the quantum nature of the interaction between photons and electrons in atoms that may be hundreds of light years away. This ability to read the composition of distant objects through the light they emitted in the past is one of the most powerful instruments of astronomy. It allows us to trace the chemical evolution of the universe over time, comparing the composition of stars of different ages and different galaxies. Very old stars, formed when the universe had only a small fraction of its current age, show spectra dominated by hydrogen and helium, with minimal traces of heavier elements. Younger stars like our Sun show a much greater richness of metals, reflecting the accumulation of generations of stellar synthesis. Ancient light tells us the story of cosmic alchemy, a process that transformed a universe of hydrogen and helium into a universe capable of harboring entire periodic tables of elements, rocky planets, and the carbon chemistry that sustains life as we know it. As an integrated system, the observable universe we see when looking at the night sky is a construction of overlapping temporal layers. The moon is there as it was just over a second ago. The sun is there as it was about 8 minutes ago. The nearest stars are there as they were years or decades ago. The most distant stars in the Milky Way are there as they were thousands of years ago. Neighbouring galaxies are there as they were millions of years ago. And the most distant objects we can detect, quasars and primordial galaxies at the edge of the observable universe, are there as they were billions of years ago, when the universe was young and feverish and completely different from the serene and expanded cosmos we inhabit today. There is no image of the universe as it is right now at this moment. That image is physically impossible. The reality we observe is always a mosaic of different pasts, a collage of distinct epochs assembled by the finite speed of light. The system does not have a unified, observable present state. It only has histories that reach us with delays that depend on distances. This is not a technological limitation that more advanced equipment will solve someday. It is a fundamental characteristic of the structure of space-time, inscribed in the equations that govern the propagation of information through the universe. The emergence of complex patterns from these simple rules is especially visible when we consider how all of observational astronomy, all our knowledge about the cosmos, emerge from the simple rule that light travels at a constant and finite speed. From this single rule emerged the notion of the cosmological horizon, the understanding that there is a limit beyond which we cannot see, because the light from there has not yet had time to reach us since the beginning of the universe. From this same rule emerged the notion of the observable universe as a bubble around us, not because we are the center of anything, but because we are the reference point of our own observation. From this same rule emerged the technique of using telescopes as time machines, the understanding that looking far is looking back, and that therefore we can study the history of the universe simply by building more powerful telescopes. And from this same rule, followed in all its implications, emerged the disturbing and beautiful understanding that we will never be able to see the universe as it really is, only as it was, and that this condition is permanent and universal and shared by any observer at any point in the cosmos. There is no privileged place, no point of view that escapes this limitation. Every being that looks at the sky, in any galaxy, at any epoch, is looking at the past. The contemplation of the universe is always inevitably a meditation on time. Deep down, seeing stars that no longer exist is simply the universe remembering itself. It is reality leaving traces of its own history inscribed in space through light, and it is consciousness, emerged from stardust and carbon chemistry and billions of years of evolution, discovering that it can read these traces. The unifying principle of everything we explored is this: information travels, time passes, and the present we observe is always a composition of pasts that reached us with different delays. The universe is an archive of itself. Every ray of light is a message. Every star we see is a story that crossed space to reach us. The fusion in the stellar core that we discussed, the radiation pressure against gravity, the delicate balance that keeps a star shining for billions of years, all this is the mechanism by which the universe writes its messages. The death of the star, the supernova, the dispersion of elements through interstellar space, all this is the universe preparing the materials so that in the future these messages will have receivers, and the existence of eyes and minds that look at the sky and wonder about stars that no longer exist is the universe reaching a point where the messages it sent to itself begin to be understood. Every element of the parts we travelled through tonight converges on this point. The speed of light is not just a cosmic speed limit. It is the mechanism by which the universe transmits its history. The expansion of the universe is not just a fact about increasing distances. It is the context that determines which messages can still arrive and which are lost forever beyond the horizon. The life and death of stars are not just physical events in distant objects. They are the chapters of the history we are receiving in delayed time every time we look at the sky. And we who look, who ask, who build telescopes and spectrometers and radio telescopes and gravitational wave detectors to amplify our ability to hear the messages the universe sent, are the part of the universe that learned to read its own writing. This is not a metaphor. It is the most accurate description we have of what scientific consciousness represents in the cosmic context. We are the way the universe found to contemplate its own history. This now dissolves into something quieter. Greatness gives way to silence. A very distant star emits its last light. This light leaves in all directions, expanding in a sphere that grows at the highest speed that exists. For millions of years it travels without encountering anything, just the slightly non-empty vacuum of interstellar space. It crosses the halo of our galaxy. It traverses the neighborhood of the solar system. It meets Earth, crosses our atmosphere, and tonight it landed in your eyes while you looked at the sky. Or it is still traveling, waiting for the moment a human gaze will receive it and complete its billion-year journey. You are safe. The light that travelled all this way reached a place of calm. The universe takes care of you with the same law that takes care of everything. The same gravity that holds galaxies together holds you here, now, in this moment of rest. The same physics that governs the stars governs every beat of your heart. Everything is in order. The cosmos did not stop while you listened to this story. It continues, as it always has, in its vast and patient processes. While you rest, the stars continue their silent work of fusion and shining and dispersing light throughout space. They do not know we are here. They do not need to know. They simply shine, and we simply receive. You are part of this. You always have been. The atoms in your body were forged in the cores of stars that died before the sun existed. You are literally made of ancient light, ancient fusion, explosions that happened so long ago the number does not easily fit in the mind. This origin is not abstract. It is you now, breathing, resting, existing. The question that brought us here, why we see stars that no longer exist, has an answer that is also an invitation. We see these stars because their light traveled to us, because space allowed this crossing, because time did not erase the message, because we exist to receive it. This set of conditions is so improbable it seems impossible, and yet it is exactly where we are. Let thoughts become slower now. Like stars moving away, each idea can gently move beyond the horizon of your attention, without hurry, without resistance. The universe is ancient and patient. It existed before you and will exist after. But in this moment, it exists with you, and you exist in it. And this coincidence of existences is the greatest of mysteries, and also the greatest of comforts. You are safe. The universe embraces you with its vastness. The stars continue to shine. Some of them no longer exist, but their light still walks. You can rest while it travels. Everything is in order in the enormous and silent cosmos. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well,